Hi everyone, welcome back to the third video of our series, Generative AI Made Easy. In this series, we are exploring how to simplify generative AI concepts using social media content automation as a practical example. In the last video, we explored how to set up the environment, how to self-host n8n, our workflow engine automation of choice. In this video, we will explore how to run LLMs locally, how to integrate them with n8n, and how to generate stories for our video. And as a bonus, we'll create an AI agent that leverages tools and Model Context Protocol (MCP) to showcase the power of AI agents beyond just story generation. Let's get started. All right, why run LLMs locally in the first place? Well, there are multiple reasons. First, to keep our data in our machines. It is more cost-effective. Some will argue with that. We can run our models locally without the need for internet access. We have more customization capabilities and more control over the inference process. And most importantly, to learn, to understand the behind the scenes of LLMs inference. And in order to run LLMs locally, we will need an LLM Runtime Engine. These are specialized software frameworks designed to effectively load, manage, and run large language models. Some of their key functions include optimizing inference performance, reducing memory requirements, providing APIs for applications to interact with the models. In this case, it's going to be our n8n interacting with local models. And of course, managing the models loading, unloading, and the inference. In reality, there are only a few inference libraries, and many are front-end tools to these inference libraries. The most famous one for running LLMs locally is llama.cpp. Whether we are using it directly or using it indirectly through many popular front-end tools, it is what's empowering large language model inference in most of the consumer hardware. If we check their GitHub repository, they are very actively working on it. Almost every few hours, there is a new patch or a new release. They have very good documentation. And the Llama server is an OpenAI compatible chat endpoint. It is very customizable. We can almost change everything on it. Like, for example, to enable flash attention. We can also specify how many layers we can offload to the GPU. By default, it runs only on CPU. And we can specify the layers that run on the GPU using this argument. And also we can change, for example, the context size. We can also run it as Docker Compose, and we will see later on how. And with the recent update, it now supports multimodal models as well. So a huge shout out to the team who developed this and made this available for the community. They are the real stars of running LLMs locally. Another very famous inference library is vLLM, a high-throughput Python-based serving engine using their page attention for efficient GPU inference. It is also very well documented. We can check in their installation. We can run it on GPUs, on CPUs, and also like other AI accelerators like Google TPU, for example. And similar to llama.cpp, it's very customizable. We can run it using Python directly, or as a Docker container providing OpenAI compatible endpoints. I personally think of vLLM more of an enterprise level solution. For example, when we start vLLM, it will auto-load the model and it will keep it on the memory ready to serve any API requests. That's very important for enterprise because it cuts on latency. But that's a little bit less convenient for us, the people who would like to run it on our own hardware. Another famous inference library is MLX, which is dedicated to run on Apple devices on M series chips. Of course, there are some other few inference libraries that we didn't mention here. We just mentioned some of the few popular ones. Now, the front-end tools are software that build on top of these inference libraries, specifically on top of llama.cpp, and provides other capabilities. For example, Ollama, a very popular solution, is more of a beginner-friendly LLM runtime engine and offers OpenAI-compatible APIs. What differentiates Ollama is its ease of model management where we can use simple commands to load multiple models and to run multiple models at the same time. A new contender in this space is Docker Model Runner. They have a bit of features to enable models to run directly on Docker, so we don't really need any other software, apart from Docker Desktop, which we use to run containers anyhow. It is a very promising solution. We will take a look into it in detail and how to use it using multiple ways. The final solution that I will talk about but will not cover during today's video is John. It is an AI chat application based on llama C++ again, and it can integrate with both local engines or cloud-based solutions like Gemini, OpenRouter, ChatGPT, etc., etc. It is a very simple solution, very straightforward one. Give it a try if you don't want to mess around with CLIs. It has built-in chat interface with many customization. You can directly customize it on the fly on the UI, or you can also run it as a server to serve models using OpenAI compatible HTTP server. Now that we have made the difference between the inference libraries and the front-end tools, let's start with Ollama. It's the simplest to start with. And in order to set it up, we can either download an installer from their official website, or we can set it up as a container using Docker Compose. That's always my preferred way of running services. It is very simple. We'll just need of course, to pull the image, give it a name, and then we'll need to set up a couple of environment variables specifically to expose the GPU. Optionally, we can expose it to the host network. In our case, we will not need that, so I will not be doing it. And then we will need a volume to store the models that we'll download using the CLIs later on. A very important note here is not to use Windows file system to mount the models or any large files in general. This topic is covered in the best practices section in the WSL integration of Docker documentation, and it clearly says the performance much higher when bound mountings from Linux file system instead of from the Windows host. That is because the WSL and Windows are completely two different hosts running on different file systems. And if we bind mount the Windows folder to a container, again, specifically for large files, then that file needs first to be cross-copied between file systems and then to be loaded to the GPU in our case. And that will cause a huge delay in loading the models every time. So avoid that. Either use Docker volumes because they will run into the WSL subsystem, or if you prefer to use folders instead of volumes, then the solution would be to create a new WSL distribution to set the version to version 2 of WSL. And then in Docker, under settings, resources, WSL integration, we need to specify the distribution that we created, not the default one. And then finally, you can create any folders there and then map them to your containers. And that will provide you the same performance as using volumes. We'll just use a volume because we will manage the models directly using Ollama CLI. We will see later on how. Then we will need to expose the GPU to the container. Finally, we will need to specify the volume that we will be using here. So we will create a new volume and we will be using it here. Let's do that very quickly. So we'll copy this and go to Visual Studio Code. The last time we set up n8n and we set up Nginx Proxy Manager to enable custom domains and SSL certificates. Now we will add Ollama. Let's give it a try. As we can see, the container has started. If we check the containers extension, we'll see that the container is running. We can now pull the models and run them locally. Let's first take a look into the Ollama website. We'll see that we have a list of models. We will need a model that does tools. We'll explore later on why. And I have a ton of success with Qwen 3. It is a very capable model. It has a variety of sizes, all the way from 0.6 billion to 235 billion. In our case, the 8 billion is more than enough. There is also the 30 billion mixture of experts, a very lightweight one despite its size. It is also a very capable model. And the 32 billion is a dense model. It requires at least 24 gigs of VRAM. And if we click on the view all, we'll see more quantization. We can check there are different quantization for all of the model sizes. And for each of the models, we will find Q4 key M. That's, I think, the most popular one that is being used. We can also choose a higher quantization, for example, Q8 or FP16. But of course, as you can see from the sizes, the Q4 QM is at 5 gig, while the other two are at 9 and 16 gig respectively. Personally, I'm using the Q4 QM, and I can say I don't notice too much of degradation of quality, while definitely there is a clear advantage on size to fit more on the GPU. The latest is just an alias for the 8 billion Q4 QM. So whether we choose the 8 billion Q4 Q medium or the 8 billion, or we choose the latest, is exactly the same. If we click there and take a look, we'll have more detail about the model. As you can see, it's a Q4 QM quantization. We can also check how many GPU layers are there. In this case, it has 36 GPU layers. If you remember from the first video, when we saw the high-level overview of a neural network with input layers, hidden layers, and output layers, those basically are the GPU layers. And in this case, Qwen 3 8 billion have 36 GPU layers. We can also see the context. It has 40K context. We can also take a look at its default parameters. As we can see, the temperature by default using the Ollama version is set to 0.6. In our case, we will tune a little bit the temperature. Higher temperature will provide more variety on choosing the words, and that's definitely good for our story generation later on. In order to pull the model, if we have used the Windows installer, then all what we need to do is to open a terminal and type Ollama, and it will show us the list of possible commands. And if we use the container, then we need just to exec into the container and run bash. Then from there, we can run the Ollama commands. We will continue using the container of Ollama because that's my preferred way of running services. Now, first thing we need to do is to pull the model. So let's run Ollama pull and then the model name. In our case, it's Qwen 3. It will take about a couple of minutes to get it pulled. And then we can run it either using directly run and then ask the question that we want. We can also run it in an interactive way. The verbose mode will provide us a little bit of more information. For example, how many tokens are we generating per second? So let's try that. And let's ask it to write a short story about a cat. It's worth mentioning that Qwen 3 is a thinking model, so it will first think and then provide us with the output. And we can see that it generates an output at around 88 tokens per second. That's because I'm recording currently, so I'm taking a little bit of the GPU. Usually I'm running at 90 to 100 tokens per second. It's still a very solid speed for running models. Now, in order to exit, we click Ctrl-D to detach from the interactive mode with Ollama. Very similar to Docker commands, if we would like to check the running models, we click Ollama PS. We see that the Qwen 3 latest is running. Now, if we want to stop it now, we can run simply llama stop and give it the model name. Similar to pulling the models for Ollama, we can also pull it directly from Hugging Face. So the models in the Ollama website, those are provided by the Ollama team themselves with their chat templates, etc. But also we can get more from Hugging Face, from official sources, but also from community members. If we go to Hugging Face, go to the models, you will see there are many categories. In today's video, we are interested into the text generation. So we click on the text generation. And we will see that Qwen 3 models are one of the very capable ones currently. So let's go to the Qwen 3 8 billion model card. We'll find a lot of information here, including the number of GPU layers. As we saw from the Ollama website, it is 36, and a bunch of other information, how to run it. What we are also interested in is the quantization of the model, because less resource requirement. with a little bit of quality degradation compromise, but it's definitely worth it. We can see that we have a lot of quantization. Some are from the Alibaba team themselves, and others are from community members like Ensloth, one of my very favorite teams. Or also Bartowski, I hope I'm spelling his name correctly, is also a very active community member who provides very good quality quantization. I will go with the official Qwen 3.8 billion. I don't think many people noticed this button here, but if you click on the use this model, you will find different ways of running the model with different applications. In our case, Ollama, we just click there, and it will provide us with the command that we can copy to pull the model or run it. We can also customize the quantization. In this case, let's go with the Q8 just to compare it to the Q4 performance. Let's copy that, head back to the terminal, and paste that command. It will take, of course, a little bit of time. Let's run it with the verbose mode to see the generation speed. And let's ask it the same question. We can directly notice that it is slightly slower. And we can see it's a lot slower, from solid 87 tokens per second to 60 tokens per second. This is still not the FP16 or the original size. This is still a quantization, but at Q8. That's why I personally prefer the Q4KM. It provides a very solid results with a faster generation time. But of course, it depends on the use case. If your case requires the Q8, then go for it. Let's again check the running models. We'll see that that model is running. So let's stop it. And let's delete it. So if we check again the available models, we will see only the Qwen 3 latest available at this point. That covers the basics of Ollama, and as you can see, it's very straightforward, easy to deal with. From their website or from Hugging Face, we can pull models and we can run them. And personally, I didn't face issues with Ollama, so I definitely recommend it for users who are starting with running LLMs locally and are looking for an open source solution. The real stars, the Llama C++ team and their Llama C++ inference library. In order to run it, we have a couple of options, either using a binary from their GitHub repository. And as you can see, it's available for macOS, Ubuntu, and Windows. I will need the CUDA 12.4 binary. So in order to run it as a server and provide OpenAI compatible APIs, we can use the Llama server binary using Ginger to enable auto tools selection. We can enable flash attention. In this case, I'm offloading all layers. If you remember, Qwen 3 has 36 layers. So by setting 99 layers, basically we are setting all layers to the GPU for faster inference. And then we can specify that it will run on the local network on port 8080. And in this case, we are getting the model directly from Hugging Face. We can also set it up using Docker Compose. There is a Docker image for that. Very important to set some of the environment variables similar to the commands here. First, to select which model to download. In this case, we are getting it directly from Hugging Face. Or if we have it already in our system, then we can specify the location of those models directly with this environment variable. We can also specify the context size. So by default, it is 4K, and we can set it to 0 to get it directly from the model. We are offloading all layers to the GPU. We are setting Ginger for auto tool selection. We can also expose the port because it has a chat UI that we can access. Then we specify the volume, and then we are exposing the GPU to the container. Let's give it a try. In this case, let's use the binary. So I have it already downloaded. I put it under C. And if we run the command, it will load the model, load the chat template. And then now it's running on port 8080. So let's go there. As you can see on port 8080, we can customize the settings, temperature, etc. directly here. And something that we can enable is the tokens per second to measure the performance of this. Let's give it a try, ask the same query as before. I like the simplistic UI interface. Thought process is hidden by default. And as you can see, it's running a little bit faster than Ollama on the container. So instead of the 87 tokens per second that we got earlier, this now is running at 95 tokens per second. So a slight speed improvement clearly here. The next promising solution I would cover is Docker Model Runner. It is still in beta, as we said. And in order to enable it, we need to go to the settings and features in development. We can enable Docker Model Runner, and we can also enable GPU backend inference. Otherwise, it will run on CPU. We can also set the model to be available to our local network, not only to the Docker network, by ticking this option, and we click Apply and Restart. Now, after that, you will see that we have a new tab here called Models. I've already got the Qwen 3 downloaded, but basically the way to download it is by either directly from Docker Hub. So Docker Hub now also hosts models, and Qwen 3 is one of them. So we can click there, and we can see that there are multiple tags for the different model sizes and quantization. We can also run the models directly from the Hugging Face. In order to do that, we can use simple commands like docker model status to see the status of the model. It's running on Llama C++, and in this case, it's using the CUDA version. That's because we enabled GPU backend inference. Otherwise, you will see that it is using the CPU version. We would like to pull a model, then we use the docker model and then pull, and we specify the tag. Or we can get it directly from Hugging Face, and for that we will do docker model pull, and then the URL to the Hugging Face model that we would like to pull. We can check the available models by doing docker model list, and we can also run a model similar to what we did with Ollama directly on the CLI. Of course, now it's loading the model, and voila, the model has been loaded and it provided us with an answer. Of course, that's not the way that we will use the model. It is providing an OpenAI compatible API, either by using the Docker Network DNS, or if we have enabled TCP host, then we can access it, of course, through the host network. Finally, we can also download the model using Docker Compose. Similar to how we define a container, we can also define a model and provide the URL of the model to be downloaded. Finally, to showcase vLLM, we can either set it up using Python or using a container. We need first to provide a Hugging Face hub token in order to pull the models. We need to provide the volume in order to cache the downloaded models. Otherwise, each time we restart the container, vLLM will need to re-download the model, so that's very important. And then finally, we need to provide the list of commands. Similar to Llama C++, we need to specify the host, the port, the maximum utilization of the GPU. In this case, we are setting it to 90%. The context length to enable auto tool choice, and also to provide a tool called parser. In the documentation, it specifies which parser to use for which model. For Qwen 3, we can use Hermes. And then finally, we need to provide the model from Hugging Face and, of course, expose GPU to the container. Now, of course, we covered how to run the LLMs locally. And of course, we will not run the models using CLI chat. We are more interested in integrating them with other applications. In our case, let's focus on n8n. We will also focus only on Ollama moving forward. It is exactly the same if we choose a different tool than Ollama. As long as it provides OpenAI compatible APIs, we just need to integrate it with n8n with a URL similar to this. We will also register it as a dedicated Ollama native node in n8n, and we will see that it provides us with extra features that are not available with the OpenAI node. Now let's open n8n and let's integrate it with Ollama. And as you can see from the dashboard of n8n, we will see workflows. I've already prepared some that we'll explore together. We can also create credentials to integrate with other applications, like in this case, Ollama. And we can have a list of executions. That is, whenever we execute a workflow, it will be registered with its status, the start time, and how much time it took. Now, in order to create a credential, we just need to click here and create credential. As long as we are running an inference engine that provides OpenAI compatible API, then we can integrate it as an OpenAI node. We'll need to provide an API key. If we are, of course, using the OpenAI public instances, then we need to provide the API key that we retrieve from them. But in our case, because we are running locally, we don't need an API key. So we'll just put any text, doesn't matter. And then here on the base URL, we will change it with HTTP, Ollama, the port, and then v1. Quick save. We'll see that the connection was successful. And we can customize here the name Ollama as an example. And we click save. So that was the first method. Or we can also integrate it as an Ollama credentials. That is because n8n have a native Ollama node. Similar, we do create credential. We search for Ollama. And then we provide it here. Instead of localhost, we'll just say Ollama, give it a name, Ollama, for example, and then click save. And as you can see, the test was successful. So what we did so far is running LLMs locally, integrate them with n8n, and then as an output out of this phase one, we will need two things. That is a script to be translated into a narrative audio using a speech generation model or text to audio. And then to visualize the story, we will need some images. 6 images for 30-second videos should be enough. And for each of those images, we'll need an image prompt, like what the character is doing in that specific moment of the story. Now, in order to create the narrative and the 6 visual scenes that will tell the story, we'll need a good prompt. First, we start with encouraging the model toward a specific type of storytelling. And the better detail you provided toward what style you are looking for, the better output you will get. And then we will split the prompt into 3 tasks. The first task is to write a short story. We are providing it with clear requirement about the character itself. And the story should include a clear theme like friendship, adventure, self-discovery. The second task is to create a concise 30-second narrative script. And similar to task 1, we should provide it with clear instruction. We want the narrative to be written in specified language. And then we are telling the model to structure this story according to the following timeline. First 5 seconds is a hook, just to present the character and the initial problem. Then for the next 10 seconds to provide a struggle with a little bit of humor twist. And then the last 15 seconds is to provide a resolution and a lesson for the story. The third task, that's where we will generate the visual scenes. So similar, clear task description, and then clear instruction to create 6 scenes. And then providing specific rules about each of the scene. For example, scene 1 is to introduce the character problem. Scene 2 is to show the character trying and failing at a specific task, till we get the scene 6, which will conclude with lesson and takeaway from the story. And then very importantly, to include the full exact character description in each and every scene, which will help later on in the image generation to have a very consistent character. And then finally, we are providing it with the desired output format. So now let's go back to n8n and let's run this. That is going to be our story generation level 1. As you can see, I have already prepared an OpenAI node. As this is level 1, let's just keep it simple. We choose the credentials that we created earlier. And then for the resource is going to be text generation. We'll explore image and audio generation in future videos. And then the operation is to message a model. We selected the model by ID, got it from Ollama. That's the one that we downloaded earlier, Qwen 3 latest. And then for the prompt, we provided the different tasks that we described together and we provided the system prompt. It's always better to provide system prompt. It's important to enable this so that we are asking the model to output the content in a JSON format. Let's test it. We got a JSON format with the content that we asked it for. As we asked it, the narrative is plain text. And then for the scenes, we have 6 visual scenes. And each of them is describing the character first and then providing what the character is doing. Now, something to note here. First, the character was more described in the first scene than the second one. And then the second note here is in the first and second scenes, we got a scene description key and then the value that we are looking for. While in the third one, it skipped the key scene description, just provided the description directly. This doesn't align 100% to our request. And also it will break the pipeline later on, because if we start using the scene description as our key, it will not find it here and it will break. That's because we are not enforcing any output requirements. We are just asking the model to do it like this. The model will try its best to respect it. So if we run it enough times, we can get a good result like this one. So we have the different scene description keys and a good description, but we are always relying on the model to understand our request and to provide exactly the output that we are looking for. And this is the downside of the level number 1. It's a single prompt that will both generate the scene descriptions and the narrative. Second is we are just asking the model to output the format we are looking for. We are not enforcing anything. And then thirdly, the character description here between the different scenes, although very similar, it's not exactly what we are looking for. So let's move to level 2, and that is with structured output with an AI agent. So we'll use now an AI agent node instead of the OpenAI node, and we will use a structured output parser. This is a method of enforcing a specific desired output from the model. So it's not just we are nicely asking, we are enforcing a specific format. And if the agent doesn't output it like that, then it's going to error out and the agent need to redo it again. So let's go to the level 2 workflow. This time we are using an AI agent. It's very simple to create it. We just click the plus node, click AI, and then AI agent. By default, it will ask for a connected chat trigger. We will not use that now. We'll just say that we will provide the prompt below. And then we will add also a system message. We will provide a more descriptive system message. Also, we will require a specific output format. This is where we will enforce output parser. n8n provide more documentation around that. So if we click here, very similar to the first AI node, but this time instead of using the OpenAI node, we are using an AI agent. Same system message to encourage more creativeness. And then for the user message, it's the same 3 tasks we discussed together. The difference here is we'll require a specific output format. By default, it will add this 4th integration point here. We click plus and we have 3 different tools to enforce an output. It's the structured output parser that we are looking for. And let's connect it back again. And let's take a look into the structured output parser. We can enforce a specific output format that we are looking for, either by providing an example of a successful run that we like it and we would like the model to follow, or by defining the specific parameters we are looking for as JSON. It's very simple. We don't really need to write any of this. What we need to do is just take a successful run and then provide it to ChatGPT or any large model, and then ask it to transform it to a JSON schema format. So in my case, it provided me with this one. So it's a type object that we are looking for, a JSON, with different properties, 2 of them actually, the scenes, and then the narrative. And then for the scenes, we are asking about an array with exactly 6 scenes. And each of those will be an object that have an entry called scene description. and the content of that scene description would be a detailed visual description of that specific scene. We are saying that the scene description is a required parameter. At the end, we are saying that the scenes and the narrative are required and no additional properties should be given. Before giving it a try, we need to specify chat model by providing a chat model node here. As you can see, n8n supports a wide range of popular chat engines from Anthropic, from ChatGPT, from DeepSeek, Google, but also OpenAI and Ollama. We can integrate it directly using Ollama. And from the Ollama account, we can choose which model to run. Or because it's OpenAI compatible, we can also attach it to an OpenAI chat node. And then similar thing, we will just choose the account we created. And also we can choose from a list and we can choose the model that we are looking for. We are also increasing the sampling temperature to get more creative outputs. We are looking for a specific response format like JSON. I'm satisfied with increasing the temperature to 0.9 and then to ask for a JSON output. We can compare it very quickly to the Ollama chat model. You can see that we have also the temperature that we can change to 0.9. We can see that also we have the output format, but to be JSON, but also we have more specific Ollama settings, like to run it as a low VRAM mode, to do a context length. We can change more settings using the Ollama node because it's dedicated to Ollama. In our case, we will just change the temperature and the output format to be JSON. So either off should be fine. So I will keep going in this example with the OpenAI chat model. Now let's give it a try. We can click test workflow. So it was a success. Let's take a look into the output. We can see that it is providing us with a table of scenes, 6 items of them, and then a narrative. And then if we take a look into the scenes, we will see there are scene description key as we ask it. So that's definitely better than the previous run. Let's take a look into the logs and check how this run was done. So first we will see there is an input from the chat model and an output. The input is the system message. And then you will see here the AI agent included this automatically. It says here important. For your response to user, you must use the format final JSON response. So the AI agent is passing our structured output format as a tool to the LLM and asking it as a must to follow that specific output format. Then the human is the user message. That is where the different tasks that we provided are being passed to the model. So basically, this is the full prompt that is being sent to the LLM. And then if we check the output, it might seem as empty, but it's not really. If we check the detailed JSON format, we will see that it did a tool call to our LLM model, in this case, Qwen 3 latest, and provided us with a little bit of information about the token usage. Now let's check the tool that it called, the structured output parser, and we'll see that it provided the action to parse the output that it generated. And then we can see that the tool have took that input from the LLM that is not parsed and parsed it as exactly what we are looking for, including the scenes as a table with the different scene description, with the key of scene description. And then at the end, it provided the narrative. Sometimes it will fail the parsing according to our desired output, but that's fine because it will retry. We can configure the retries in the settings of the agent, and we can specify to retry on fail. So if it, for example, tried to parse it and didn't succeed, then in this case, it will retry 3 times with a time in between of 1 second. And of course, if it didn't succeed in these 3 times, then it will just stop the workflow. That's what we told it. This already looks good. However, let's push things a little bit more and let's go to level 3. This is where we will split the tasks into multiple agents. So instead of a single agent running all of the tasks and providing us with an output, we can configure multiple agents to work together to provide us with a specific task. So if we go now to level 3, we'll see that we have 3 agents working together. I renamed them. You can, of course, change the name here. So each of them will have its own structured output parser. We will take a look in a moment. And in this case, they will all share the same chat model. Let's take a look now into the story generation. We changed the system message to be specific to story generation. We kept the same task description. In this time, we just provided an example of an output format that it needs to be JSON with the full narrative as plain text. If we take a look into the structured output parser, it is of a type object with a single property called story. And we said that the story is a required parameter. So let's run only this first agent. And to do that, we can just click test this step. This is a good example here. Let's take a look into the output. It's the story as we asked it for. But if we check logs, we will see that the OpenAI first provided, as before, like the system message, that it must use the format final JSON response, and then the task to create a story. However, when that has been passed to the structured output parser, we'll see that it didn't fit the output format, desired output format. If we check, it includes like a type function, story. It's not the output, the format that we asked it for. And that's why it errored out. Because we configured the agent to retry on error, it retried, and this time as output, it provided the story respecting the output format, and the structured output format accepted the output. And that's why we see it red here. That's just to indicate that at least once it was failing, but at the end it autocorrected itself. Now let's go to the second task. We'll see that because we are chaining these nodes, the output of one node, in this case of one agent, will be passed to the second agent. So as input, we are getting from the node called generate story, we are getting an output with a parameter called the story. So in our example, we will pass the story to the second agent because now we are running different agents doing each one task. We will need to pass the output of one agent to the next. In simple terms, for the second agent to create a narrative of a story, it needs to know what was the story in the first place. And it's very simple. The way to pass it is we just drag and drop, and it will take it as, you can see here what the result will look like. It's seeing the full story passed in the prompt. And then it continues with the same instruction as before. That's why it's simpler to deal with JSON outputs, because it's simpler to pass to other agents. So let's try this step. It's worth noting that I changed the system message for the narrative agent. We'll see from the logs that it errored out in first try, and then the second time it succeeded, and the structured output parser accepted it. It's fine to error out. What's important is to get a precise output according to the desired state that we are looking for. And that's what we got here. Now, finally, the visual scenes. Similar thing, I changed also the system message. I will provide the workflow, so you don't really need to write it. You can just import it and run it on your system. Now for this agent, which will generate the visual prompts, we have the task, which is to translate the story into 6 different scenes. Similar to before, we will also need to pass the story. So let's give it a try. And we can see that we got our 6 visual scenes in the format that we are looking for. Something that we can enhance is the way that we pass data from one agent to another. We are passing it statically. we need to tell each agent that this is the story that you need to create a narrative for, or you need to create visual scenes for. That is where memory can come in handy. We can gift our agents memory, and more specifically, a shared memory between the different agents. And that will allow us to skip any data passing between the different agents, because each agent will have access to the previous output from the previous agent directly from the shared memory. Also, and of course, why not, let's have two more agents to enhance the story quality itself. So we're having one agent that was providing a story, and then agent 4 and 5 was creating the narrative and visuals respectively. We can add two more agents. One is to develop the outline based on a specific format that we would like to have. And the second one is to develop the character and settings description, so then we can have better character consistency between the scenes. So let's explore our final level of story generation and the one that we will be using for the rest of the automation pipeline. So a couple of changes here. First one, we are now using the Ollama chat model. The second change is that now we have a form submission as a trigger instead of manually triggering it. I think it's more convenient for us to have an access to a form to customize the story generation each time. So let's take a look into the form. We gave it first a field name called topic of type text area. And this is where we will customize our story. Instead of having random story each time, we can have the user input the topic of the story that he's looking for, and then let our AI agent develop it into visual, narrative, character consistency, etc., etc. The second option that I would like to provide is a language. So instead of having our stories always being generated in English, we can customize that and then let the user choose. And let's give it a test. If we click test, this is the form that we will see. As we develop the workflow later on with image generation and video generation, we'll provide other options for the user to choose, for example, which image model to use for image generation, which video model to use for video generation, and any other parameters that we would like the user to fill. So for example, as a topic, we can put an astronaut cat visiting the moon for the first time. Let's see what the AI agent can do about that. And then for the language, let's put English. And then let's click generate video. Once we submit this, we can see that the output contains the topic and then the language. And then of course, we can use this later on with our node. Let's pin this. Pinning it means it will conserve its status for the next run. So I don't want to refill the form every time for our testing. But of course, when we publish it as a production, we will unpin it so the user can fill it every time. Now for the story, we will keep the same system message, but we make a small change. We will say about and basically drag and drop the topic here. So in this case, about an astronaut cat visiting the moon for the first time. And then the rest of the prompt should be exactly the same. Let's hit test. And we can see here that the model have started with an introduction and then start talking about the astronaut cat. So it respected our output. Now, if we take logs now, we'll see that first it loaded from the memory. That's because now it has access to memory. I will come to this in a moment. So first it consulted the memory. Do I have anything in the memory? Of course, as this is the first run, it has nothing in the memory. So the output was, nope, it's empty. So it continued with the same as before, the system message. It passed then the output to the structured output parser. And then what we will see here in the simple memory, this time it provided as input to the simple memory to save a context, with the input being the user prompt, the system message, the formatting instruction, and then the output of the node. So basically it saved everything from the prompt to the output. So that's what the memory will provide us. It will provide us with a shared space In our case, we want to share the memory between the agents, and that's what the memory will help for. Avoid passing data statically between agents. The agents will have access to the same memory between them. So that's the input that we got from the agent to save, and that's basically what the memory did. It's worth mentioning that the simple memory will require a session ID. That is because it's not long memory. As soon as the session ends, all of the stored data, of course, will be deleted. So this is more of a short-lived memory. And for the key, I'm providing it with the execution ID. This is a global variable that n8n provide to identify the execution of this workflow. So all what we need to do first time is to click the plus button. It will ask us what kind of memory. The simple memory is the short-lived memory, or we can choose a database or a cache as a memory, and this would be more of long-lived memories. But of course, then we need to have a separate instance of Postgres or MongoDB to be used to store the status. Yeah, this is new one. This is the one that will develop the narrative outline. So let's check it very quickly together. So we are asking it to clearly define typical areas of any storytelling, the hook, the conflict, the turning point, the resolution, and then call to action. And that will enhance the quality of our storytelling because it will have the 5 pillars of storytelling in general. And as a system message, as always, we are providing it with a dedicated system message to encourage it with that specific task. So in this case, you are a narrative architect skilled with inserting stories into their core structured elements, etc., etc. Let's give it a try. So we'll see that it provided us with the 5 pillars from the hook till the call to action. What if the universe was calling you to explore? Would you answer? Yeah, maybe. And if we check the logs, we'll see that similar to before, it first retrieved the memory. So we'll see that it took as input the load memory variables and it loaded everything from the memory. And that, of course, including the system message, the formatting structure, but what's important is the story that it will need to deal with. And as you can see, the AI agent provided the output of the previous node from the memory, retrieved from the memory to the agent, and then provided the instructions and the output. And that's the output format that we got. It got it through the structured output parser just to make sure that it is respecting output. And then finally, it saved it to the memory, so save context. And now we have a memory updated with both outputs from first node and second node. And that's why we see 4 interactions with the memory, read, write, and that's the 4. If we continue with the third node, this is where we will develop a character. And if we can see here, the task is to generate a precise visual description. And then, similar to before, asking it to output it as JSON with 2 elements, the character and the settings. Providing it with an example is always helpful. Now, the narrative one is the same as before. The only difference here is that we will specify the language. If you remember, before we were just specifying English as a language. Now we will let the user decide. And even better than that, we will also do a default. In our case, it is set, so that's why it picked English. But if the user didn't input anything, then it's going to default to French. And then finally, the visual scenes is exactly the same. The only difference is that we don't really need to pass the story anymore because it's going to retrieve it from the memory. And then lastly, on top of the scene description, we are adding now a new key called character, and that's going to be the character that we have developed from the character settings here. So we are taking the character as is and passing it to every single scene, and that will help us now have the same exact character description in every scene. Now let's run the model end-to-end and let's see how much time it will take. So it took around 25 seconds to run the whole thing. In general, and if I'm not recording, it takes about 15 seconds to go through the full 5 agents. And I think that's very respectable time to get a quality story and a character consistency. So as you can see now in the output, we'll have always the same character between the different scenes. That's because we have a dedicated AI agent doing that. And then for the description, that's what the character is doing for that specific scene. So the same character with different scene description, and that's exactly what we are looking for. Before we conclude, I just wanted to expand a little bit on the capability of AI agents, because although we covered how to use memory, how to use the JSON output format, the AI agents are capable more than just that. So for that, I have created an AI chatbot that have access to a model. It's actually the same 138 billion model. We gave it memory to remember interactions between chats. And in this time, instead of using the n8n form, we will use this message node that will allow us basically to chat with our model. This, of course, is just for the example. In reality, I would suggest using it with a Telegram trigger message, which will allow us to chat with our AI agent from distance using Telegram. Now, in this example, we will just use the local chat node just to showcase the possibilities. We have also exposed some tools. These, of course, are just to show the potential. In reality, if you click the plus, and you will see how many tools n8n have access to. And then on top of that, if we start using MCP or Model Context Protocol, I will not cover it in this video. I will talk about it in a dedicated video. MCP seems to be the standard for the future for AI agents, or how AI agents interact with tools in the future. In the last week, both Google and Microsoft announced that they will support MCP. For now, let's just say that our AI agent now have access to multiple tools. Now let's try to chat with our AI agent. First, we will just say hi. Being polite with AI agent is important. I would like to ask about the weather today. As you can see, we didn't tell it which tool to use, but it auto-discovers all of the tools that it has access to, and then it decided to use this one to retrieve the weather data. And here then the AI agent provided us with the temperature. Let's now ask it a different question to search about Model Context Protocol on internet and GitHub. So again, we didn't specify which tools to use. And we can see that the AI agent have run both tools at the same time to retrieve more data. And we can see here that it sent a query to Brave with Model Context Protocol. Then Brave provided the data. Same thing for GitHub. It asked about Model Context Protocol, 20 results. And then it processed all of that and provided us with an output about Model Context Protocol. Now let's ask it a different question. Let's ask it if I have anything important in my inbox. Again, it has access to multiple tools, even from Gmail, but it chose to use the one that will provide it with all emails. Now it's processing all of those list of emails, and it's summarizing to us the critical alerts and actions and pending tasks and communication, etc., etc. Finally, let's ask it something fun. Let's ask it to find listings in Airbnb in Tunisia, between mid of July till end of July. And let's see. Again, it asked Airbnb tool about check-in date, checkout date. Of course, because we didn't provide more detail about how many children, it assumed that it is 0. And then the location, and then the room type. It made some assumptions there. And we can see that we got some data from Airbnb. And then the model will process them and then output the data to us. I think what's important in this very quick demo is just the capabilities of AI agents. It's not just to generate a story in a specific format. It can be exposed to multiple tools. It can choose which tool to use. It can plan the way to approach our questions and then provide us with data. Also in the MCP, we didn't cover everything. In this case, we chose only 3 specific tools and provided them individually. We can provide multiple tools as a single library and then provide it to the AI agent and let the AI agent list the tools, list the description of each of those tools, and then decide which one to use. Let's also not forget that we are using a relatively small model here, an 8 billion. And even with that, we're able to get consistent results on this tool utilization. The Qwen 3 8 billion is a small capable model, but that doesn't deny that if we were using a bigger model and more capable model, then we will get even better results and better tool utilization. As promised, I will be providing the workflow that we created today with all of the agents in the video description. Also, stay tuned to the next video, which will be about image generations. We will take the visual scenes prompts that we created in today's video, pass it to multiple local open source models, and generate stunning images out of them. I promise also to publish a video about MCP and how to use them. So yeah, subscribe to the channel, and thanks a million. See you next time.